All right, I have the great honor of introducing Stacy McGaugh. He is a current professor at Case Western Reserve University, where I did my grad school, and Grace did her undergrad. So he's very near and dear to both of us. This is basic CV. So he got his PhD from the University of Michigan. Then did a variety of research positions at Cambridge over the UK, at the Carnegie Institute of Washington, and at Rutgers, before landing a professorship at the University of Maryland, where he was there for about 14 years, and he's been at Case Western since 2012. He is an expert on low surface brightness galaxies, the baryonic Tully-Fisher relation, as well as modified Newtonian dynamics, MOND. Although I think still his most widely cited paper is his strong line abundance calibration that he did back in the 90s, which he doesn't do anymore. You'll probably hear about that to plug my own talk on Thursday in the XGal group. But without further ado, I'll hand it over to Stacy to talk to us about galaxies that are too big too soon.
Thank you, Ray. Thanks for having me. Done a few Zoom talks. Of course, coming out of COVID, a lot of places prefer to operate that way for obvious reasons. I don't. I like to visit people and talk to you in person, so I'm happy to be here. I don't like to dwell on citation statistics, but since you mentioned it, I wrote that paper as a grad student. And only last year did one of the reviews overtake it.
Okay.
It depends on who you ask. If you ask NASA ADS or if you ask Google Scholar or something. But so basically what he's saying is that I peaked early in just like some galaxies in the early universe. So I want to try to connect some very disparate things here, and it probably won't work, but you're stuck with me now. So I picked this title because there are some regularities in the kinematics of local galaxies that I think are an important clue to what's going on in the universe that led to a connection to what we're now seeing with JWST in the early universe, things that I started thinking about when JWST was being proposed under the cheaper, faster, better mantra. That was a complete disaster, but nevertheless, it got done. And a quarter century later, we're finally able to see the fruits of that long labor of many, many people. Here's a nice, pretty spiral galaxy, NGC 6946, pretty star-forming region, small bulge component, maybe 5% of the total light, depending on what wavelengths, nice, pretty spiral galaxies. And of course, we'd like to know how this thing came to be. How did it form? How does it evolve? I know a lot of you work on exactly those sorts of things. So I started out working on low surface brightness galaxies and quantifying this sort of thing. I didn't show you a low surface brightness galaxy because they're boring. That's pretty right. But of course, you can fit ellipses to these kind of images. There's a image from the Spitzer Space Telescope. This turns out to be a good bandpass to trace the stellar mass. And one typically fits an exponential disk to these kind of light profiles and pulls whatever's left over a bulge. Argue about that all day. But what's useful here is that you can quantify the entire image of a galaxy and sort of boil it down to a few parameters, in this case, a central surface brightness and a scale length. How fast does the light fall off? That's really, really useful for sort of a gross characterization of galaxies, and it's kind of dangerous for other applications, as you see. So one gross characterization is just how big are galaxies? So this is the scale length measured for a sample of spiral galaxies from Stefan Courteau. It's a function of stellar mass. And you see there's a big blob of points there. There are lots and lots of galaxies there. And that corresponds to the raw numbers that you see in magnitude limited surveys, like this is the number from Sloan, whatever DR, when I went and made this plot. And this is, of course, a competition between the fact that there is a real cutoff. You don't have 10 to the 13 solar mass individual galaxies. So this is the cut off in the luminosity function. But on the other side, the numbers are going down just for selection effects. These things are faint, so you don't see very many of them, whereas these things are bright, you see lots of them. So you need to correct for that. And of course, people create luminosity functions to do just that. And I've been concerned much of my career for what happens at the fainter end. So low surface brightness means large, so larger scale length for a given luminosity, and that typically goes hand in hand with low luminosity, but there's a lot of scatter there. Sometimes you have low surface brightness galaxies that are pretty big, and things live all over this. And so there are a lot of things we want to know the properties of here. There. And let's correlate with type. The early type spirals live typically in this blob, and the irregulars, SDs, live in this part down here with a little bit of crossover at SCD. So, you know, that's sort of where things live all over this mass size plane. And there are just a few examples. Our own Milky Way lives in this blob. It's a fairly typical spiral galaxy, or maybe a little on the compact side. Depends on whose estimate of the scale length you believe. UGC 2885, fairly unassuming looking spiral, one of the most massive spirals in the local universe. Happens to be some other famous galaxies. One of my favorite LSP dwarfs. And DDO 154, very gas rich, low mass dwarf, but there are other examples. So galaxies live all over this plane. So we need to understand that. And I've only so far showed late type galaxies. There are early types that lack gas. And so this is now the gas mass against stellar mass. You see the same sequence before. The early type spirals. Still earlier type galaxies, sometimes they have a little bit of gas. Mostly they're just upper limits. So these are red and dead. Used up their gas, they've stopped forming stars, but they're massive. Up here, I'm sure it's less effective. But note here that a lot of the late type galaxies, the irregulars, the SEDs, they are more gas than stars. More atomic gas there than there is stellar mass. The molecular gas is usually number 3 behind those two. That's the bulk of the baryonic mass in most galaxies, not all of them, but usually it's mostly stars over here, mostly gas over there. For late type galaxies, of course, again, there are examples of early type galaxies that have no gas that live at very low stellar masses. Things to understand. So galaxies are made of gas as well as stars. Here's our poster galaxy in the optical, nice and pretty. Here it is in the near infrared. This is the 2-mass image. The bulge component is a little more apparent to the eye in this one. And this is a better map of the stellar mass seen through the dust at some level. But also this is just more robustly related to mass. But then there's the atomic gas, and these are all to the same scale. So it's really what you see, that the atomic gas is more extended, and that's fairly typical for local spiral galaxies. So we want to understand the mass components of these things, the distribution of gravitational force from each component, which add linearly in standard Newtonian theory, so each component independently, plus whatever you need in the way of dark matter. So here's the surface brightness profile of 46, and a couple of different pass bands. Also, this galaxy being face on has been studied. We've looked at the vertical velocity dispersion relative to inferred as mass profile. That's from Mannion et al. And that's in pretty good agreement with what you would have guessed was the surface density profile just from looking at the stars, which is what I do a lot of. So that's comforting at some level. Quick reminder of how mass models work, and some of the approximations we can make. And at some level, science is always an approximation. It's just how deep into the weeds we want to get. So the crudest thing we could do is just assume that our galaxy is a point mass. and it'll have a rotation curve like this. Okay, well, that's terrible. Galaxies are extended mass distributions. So we could at least assume they're a spherical cow. That's that dashed line. And you're just assuming that the enclosed mass follows y or whatever you're talking about. So v squared is just GM over R. And that's okay. And all of this is scaled for the case of NGC 6946. So that's stellar mass, that scale length. The spherical cow is still not a very good approximation. So you can use the thin exponential disk. So this is basically the plot that is in Binney and Tremaine, where they famously have the lines switched. So there's a spherical cow, there's a thin exponential disk. I have not switched, those are labeled correctly. And so the cylindrical thin disk has net faster rotation than the same spherical mass distribution. So it's a little boost just from the geometry, and that's all it is geometrical effect. Of course, disks are not razor thin. That formula assumes it is razor thin, going all the way back to Freeman, 1970. So you can assume some thickness based on the statistics of observations of edge-on galaxies, and just assume something on average. But it doesn't make a big difference. That thick disk is now very close to the thin disk. So, all right, we're getting there. And then you can drop the assumption of the exponential surface brightness distribution altogether and just use the actual data, solve the Poisson equation numerically, and then you get that blue line there. That's basically taking what we saw from fitting ellipses to this thing, keeping all the bumps and wiggles, solving the Poisson equation, and we get that bumps. And I've excised the bulge from this for simplicity. There is a bulge. So that's just the disk. And that is the level approximation at which I will work. We're still azimuthally averaging over the spiral arms. So you could, in principle, consider a 2D model where the potential and the mass distribution is a function of azimuth as well as radius, but then that thing is rotating with some pattern speed, and it's basically in motion all the time. So this is the best you can do with something that we're pretending is a stable equilibrium configuration. Of course, it's not, but that's as close as we can get. And you can make more elaborate models, and on Gaia data, then you really do have to worry about all those things. So I mentioned that because we're still at the point of just assuming an exponential disk for the Milky Way in a lot of cases, because we can't see it from the outside the way we can these other galaxies. So I have to keep all these things in mind, what approximations we're making. But now we can put it all together. Here's that numerically solved disk. Added in the bulge component now, and the stars, the gas, sum them up. And that solid line is the total rotation that we expect. And you notice that that is well explained in small radii. In fact, there's even a little peak there in the rotation that is predicted by the presence of that bulge. Even though that bulge is only 5% of the stellar mass, it's very compact. And since these are M over R, they still have a significant thing there. And so that matters. And you explain the rotation pretty well. And that's generically true for high surface brightness galaxies, that they're close to maximal in the sense that the stars alone explain almost all of the velocity of small radii. But that ceases to be true as you get further out. And so there is this tendency for rotation curves to become flat. And that is in excess of what we expect from just what we can see, which of course leads us to infer that the difference is due to something unseen. Now, that is sort of the level of knowledge at which point we developed the entire elaborate dark matter paradigm that we have today. But we weren't really playing with a full deck of cards when we did that. There's other stuff that we need to know that we partially knew at the time, but it wasn't clear maybe what the connections were. Those rotation curves are flat. Here's that big galaxy. It's rotating fast. Here's some examples of smaller galaxies. all these excellent data from old times. These were all taken up when I was a grad student. These were old things. These were, work on these dwarves kid. What's left of them. I thought these were really cool, so I was happy to do that. But notice you get down to these tiny things, talking 20 kilometers a second, 25 kilometers. And there's some very, very small galaxies out there. I think the record holder for rotating galaxy, something with gas, is Leo P, which is around 15 kilometers a second. And there's no indication that there's a bottom below that. Galaxies live all over this. There are very few galaxies faster than that. It's an upper limit to the mass. But the point here is that rotation curves become flat far out, and that amplitude of that flat rotation speed correlates with the stuff you can see. Stellar mass, this is stellar mass against that flat velocity. Basically, this is one realization of the Tully-Fisher relation. How fast something spins depends on how massive it is. And I've color coded the points now by whether or not they have more mass in their stars or in their atomic gas. So if you remember that mass size plane with the peak in the numbers around L star, you go out and do a survey, you find a lot of L star galaxies that are mostly stars, and you get a really nice Tully-Fisher relation. Works really well for distances and whatnot. If you look to lower masses, then things start to fall off of that. It becomes a mess, there's a bit of a curvature, and the scatter gets big, and all like that. That basically goes away if you add in the gas, right? These things are more gas than stars, so we ought to account for that in the budget. And so this is the same thing. B flat is measured here, but now the baryonic mass, so the sum of the stars and the gas, and you recover single power law relation over 5, almost 6 decades in mass. And it doesn't matter whether the mass is in stars or gas, they're all in the same relation. I find satisfactory. Why would the physics care if it's in stars or gas? And there doesn't seem to be any other big reservoirs of baryons left over. If there were, you'd see a deficit like you did here. Oh, there's a gap, the relation breaks. You didn't include the gas, you include the gas and that's it. So it's very hard to have an additional component of dark baryons in the disks of galaxies. There could be some further out in the corona because we're not measuring that far out. But this seems to be the bulk of the baryons in the galaxy. And that's it, right? The correlation is between the mass that we can see and the velocity that we get. No reference to dark matter there, even though we assume it's the dark matter is it can be flat. Kind of weird. But it's an empirical relation. So all we really can say is that, okay, rotation curves are flat, but also that flat rotation speed amplitude correlates with the baryonic mass. And you can write down a simple power law relation. The baryonic mass scales with some 0 point times the 4th power velocity. That line I have forced to have a slope of exactly 4. I did not fit it. The amplitude hit A. That's just a slope of 4. And the ideal fit is 3.95 or something like that for this particular set of data. And that's what you always find if you go down far enough. If you just fit up here, you get all kinds of slope because that's what happens when you fit a line over a very short baseline. If you have a long baseline, the slope goes to 4. I tried running in horror from that result for years and years, and it just keeps getting closer instead of further. So the fit parameter here is about 47 in astronomy units, solar masses, kilometers per second, fourth. And one of the amazing things about this is that the scatter is minimized when we use V flat. Now, most people, because it's more readily accessible, plot Tully-Fisher with a line width. Very much cheaper to obtain observationally, and that's fine to the extent that the line width is a proxy for V flat. But V flat is the real thing, and you see the reduction in the scatter when you do that. And one piece of physical intrinsic scatter that you cannot get rid of is the light ratio of the stars. In order to do this, you have to convert the luminosity to a stellar mass. You have to have some prescription for doing that, and that's never perfect. And so there's always going to be scatter here. And yet the scatter, when you account for the size of the error bars, is less than about 0.1 x, which if you ask stellar population models is sort of a minimum for what you expect in the scatter of the stars. So there's no intrinsic scatter in this relation. It is perfect to the extent that we can perceive it. That's really weird. Extragalactic correlations are never that good. Now, I wondered if we could unify this relation with things that don't rotate. So far I've just been talking about rotationally supported late type galaxies. Here are the dwarf spheroidals of the local group, color-coded by who they're a satellite of, or I'm not sure if they're in equilibrium. And you notice there is a parallel between the rotating things. There's Andromeda, the Milky Way, M33, LMC, SMC, forget the number, you know, those are the rotating things. These are the pressure supported things. Is there some simple way we can map from one to another? So if you try to build a mass model for these dwarf spheroidals, it looks something like this on the right. Here's one for Leo1. Here's one for WLM. This is an actual rotation curve for one of these things that rotate. That guy right there. But can we figure out how to map these onto those, given that these are parallel and giving up on the, I'm not going to attempt to address the alternates. But for the more traditional dwarf spheroidals, you get a mass model like this, which has a large uncertainty. Those dotted lines are just due to the anisotropy. You don't know, you can measure a velocity dispersion, but you don't know what the isotropy of the orbits is. And that's minimized. The half-life radius will result from Wolf. And then the naive thing to do is say, okay, assume the orbits there are isotropic. So you have 3 dimensions where the kinetic energy is divided up, sigma squared is, so basically your circular velocity is square root of 3 sigma. That's if the orbits are isotropic, and it's also not all the way out. It's half at an effective radius, whereas the rotation curves all flatten out further out. And in general, these mass models keep rising. So if you want to relate this to that, there are 2 things. One is what the isotropy of the orbits are, very hard to figure out, and also where on this curve are we actually measuring. And so I said, let's cheat. Just ask what we have to do to put them on the same relation. So there are the dwarf spheroidals, there's Pauly Fisher, and let's just imagine, okay, there is some number, theta I've called it here, that you multiply by the velocity dispersion to get that outer velocity. And like I say, naively, that would be square root of 3. Again, you have to assume a mass to light ratio, tested that. But then you can just ask the data, okay, what puts you on the relation? And basically for a mass to light ratio of 2, that number is 2. So it's a little bigger than square root of 3, but not a lot bigger. And given the fact that you probably want the number further out than the half-light radius. Okay. So these things do seem consistent with the same relation. You know, once you do that, and of course you don't have to have that mass to light ratio, so there's going to be a covariance between those 2 things. So this relation seems to follow to much lower velocity. And one application that you can make right away is the distance scale. Of course, Pauly Fisher has been used for the distance scale since it was discovered in the mid-70s. This is calibration that was published in part by Jim Schaubert. Francis Dewey is a current student working on this, so there will be an update on this soon. These are the local group galaxies we were just looking at. Those are not used in the calibration. Calibration comes from the subset of our database that has direct distance determinations from Cepheids or tip of the red giant branch, a couple of cases, supernova, but really tip the scale. It's mostly ERGB and Cepheids, and they're almost equally split. And we do that and we basically get 75. That's the calibration sample. We can take that calibration, which by itself gives us 73, right? We have and redshifts for all these things. So you can just do a straight Hubble relation. But we can also use this to calibrate baryonic Tully Fisher, apply it to all the other galaxies that we know B flat for in order to infer Hubble constant further out. We get 75. It went up, not down. Not that that's significant, it's plus or minus 2 point something. Tully's group finds something very similar with a much larger sample, but with line widths. So each individual measurement is less accurate. And those things more or less wash out. So we get the same answer, the same accuracy. And note that in the calibration sample, there's really no distinguishing between the tip of the red giant branch distances, Cepheid distances. So there's a lot of controversy about that. We don't see a tension there. So whatever's going on there, it's not showing up for the particular galaxies in our sample. I would just make a note that in the mid-aughts, we come to a concordance in part because you plotted up the Hubble constant and mass density, all these different constraints, age of the globular cluster, the baryon fraction, large scale structure, direct measurements of the Hubble constant, basically ruled out everything but this concordance region pointed out by Ostreicher and Steinhardt in the mid-90s, and they used it to argue then that we needed a cosmological constant. And there is a tension now between the locally measured Hubble constant and that inferred from Planck. And what's changed is the best fit values from the CMB. It basically marched down this trench of best fit, constant omega matter H cubed. Basically, if you're in this value, then you're in the Grand Canyon of chi squared. Everything to the sides are very clearly excluded. But along that, basically looking for the global minimum, the trench of local minimum. And that has happened over time. So I don't know where the systematic is. Everybody seems to assume that it's in the local measurements, but those haven't really changed. What's changed is systematically is the Planck from WMAP and even over time. And, you know, Planck data are fantastic. You really do need this kind of H naught to fit it, but you're fitting all these other things simultaneously. And so that gives me the heebie-jeebies.
Just give it another 50 years and the universe will stop expanding.
That's right. We can go down here and predict when it'll recollapse. We'll all get together at the end of the universe then. So anyway, that's a side point. Just by way of saying that it's not obvious to me that this is where the systematic is. We can talk about where the systematic might be here if you want to, but I'm not going to. And in fact, that's why I had the Lewis Carroll quote about you have to be mad here. I didn't want to deal with the distance scale because you have to be mad to go among those people. And I'm somebody who works on Mont. So, but back to data. I like this plot because you can see a lot of the systematics I'm talking about all at once in this one plot. So this is rotation curves, logarithmically, so you can see the shape here, and color coded by surface brightness. So red is high surface brightness, blue is low surface brightness. Remember, that's where I started, was working on these low surface brightness things. And I noticed this systematic that, you know, it's not just that B flat correlates with the total mass. That's just the outer part that's involved here in Tully Fisher. But there's something systematic about the entire shape. High surface brightness galaxies have rotation curves that rise quite quickly and flatten out almost immediately, sometimes even falling a bit before you go that. Low surface brightness galaxies have rotation curves that rise gradually and only slowly bend over towards something flat or 20, in which we don't observe far enough out to get there, with only a presumption that they will. So far, they always do when we observe further out, but you know, not always. But you can see the spectra, right, going from blue to red. So there is a variation in the shape of rotation curves that is entirely predictable by the surface brightness of the stars in the galaxy. So it's not just the total mass that correlates with the flat velocity. The shape of the rotation curve depends on the distribution of the baryons. And so how do we quantify that? Here are a few individual examples of rotation curves. Just P of R, the mass models I've described before, gas, all disk bulge. That blue line is what you expect for the baryons alone. The points are what we observe, and obviously there's an excess that we attribute to dark matter. Here's a bulge-dominated galaxy. Here's basically a disk-only spiral, and here's a very low surface brightness dwarf. It's actually gas-dominated over most of its radius. You can see the discrepancy gets larger as you go to low surface brightnesses. That's one of the things that drove me crazy early on, is why should low surface brightness galaxies show a larger mass discrepancy? I could see that they did. So those all look very different. And you can try plotting other things, and I've done that, but the thing that turns out to matter is acceleration. So the bottom row is the same plots, same data, but now this is the centripetal acceleration, v squared over r, plotted against the acceleration that is predicted by the baryons that we see. So basically that blue line, v squared over r. And so that dashed line is 1-to-1, that's Newton. That's what works if there's no dark matter or any other funny business going on. And so that's what you see there at small radii, high acceleration, they're basically right on, so you just need the stars. But as you get further out to low accelerations, you start to see a departure from behavior. Do the same thing for this galaxy, and we'll keep that line there for comparison. Okay, there's that galaxy. Keep both of them, keep that one on. And this low surface brightness galaxy is exclusively at low accelerations with large discrepancies, right? The amplitude of this mass discrepancy is how far off of the Newtonian line you are. And they all fall more or less together along the same thing. So we can do this for all the galaxies for which we have the requisite data. And this movie is just going to march you through 170 or so galaxies for which we can do this at the present time. Federico Velli, who made the movie, has a student, Konstantin Helbner, who's working on a sample that'll be several thousand. And so dashed line is Newtonian. You can see the full mass model, which there's a huge variety of for each galaxy, but they all fall more or less in the same spot. And I've assumed the same mass to light ratio for each galaxy to make this plot. We're not even fitting anything. We're just plotting the data as for our best guess of the stellar population mass to light ratio. And most of these things are very close to that. The blue points are the residuals of the scene you came. So every time we add a galaxy, it builds up this blue point. And eventually we just have this grayscale. So you saw lots of individual cases go by that had, oh, there's a point over here, but the density of points is really all pounded along that, what I call the radial acceleration relation. And I say that radial because it's not clear it applies in the vertical direction, but it sure seems to do so in the radial direction. And that is a fundamental part of the clue to what's going on in this problem, which we did not have when we invented the dark matter paradigm. So you can fit a function to this, right? The observed acceleration is just some function of that predicted by Newton. Not on the one-to-one line, so you can make up some function, and there are other. This one nicely, it was for historic reasons. It was the first one I tried. It worked so well. And the only fit parameter here, this is over 150 some galaxies, is this acceleration scale where you bend away from Newtonian behavior, and that's of order 1 angstrom per second per second. Tiny, tiny, tiny acceleration, 1 part in 10 to the 11 of what we feel here in this room. But that's what holds a galaxy together, typically, something of that order. And so it's amazing to me that this relation exists. There's not much intrinsic scatter. There are some outliers. There are individual galaxies that are just weird. It's astronomy, that always happens. But the vast majority of data are counted right inside this distribution. And this is weird because I can look at a galaxy, I can calculate what Newton predicts for the stuff I can see. I can predict what the acceleration will be. No reference to the dark matter that should be dominating that. You're not weirded out by that. You're not thinking clearly. That's just a fact, and it needs to be cogently explained, and we do not have such that. There are lots of claims, I won't go into them, but I have yet to see a satisfactory explanation. But we're astronomers, we don't care, we'll do things with it. So one fun thing I did with it, okay, there's just this empirical relation. We live in the Milky Way. We think it looks something like this face on, but we can't get outside to see. We are here. But we can measure the terminal velocities, that is a tracer of the rotation speed interior to the solar circle. So can I use this to back out what the mass distribution of the Milky Way is? So those red points are what one infers the rotation curve to be from the interstellar gas terminal velocities interior to the solar circle down to about 3 kiloparsecs, where I don't toss them anymore because the galaxy has a bar. And so you can fit that and say, okay, well, I have this radial acceleration relation that relates the total rotation to what the baryons are doing. And then I can work out what baryon distribution I need to generate that. And so that's what I infer the radially average surface brightness profile of the galaxy is to be. You know, it's got a bar component, shelf, I have to put that in to deal with the mass, but all the bumps and wiggles here are basically inferred from the bumps and wiggles in there, and they're probably not all real. But it's not just an exponential, is it? There are features there, and there should be features there. That's what we see in every spiral galaxy out exterior to us. And this lets us get to that, some structure of that. And so I'm like, oh, that's cool. And for a few years, it occurred to me, geez, you know, there are people who actually study spiral arms. Maybe these might correspond to real features. I should check. And they do. This is the Centaurus spiral arm. You actually mark out known features in the star counts that correspond to these features. So it actually seems real, or at least potentially so. And it makes predictions. So the fit region was just from the solar circle into 3 kiloparsecs. But once you have fit that much of it, you're pretty much integrated up most of the Milky Way mass. And so you can extrapolate, and that's the rotation curve that you predict. So basically everything outside the solar circle here is a prediction. All of the data that you see have been obtained since that time. Most of them are Gaia data. People have made a big deal that there's this kink here and this falls a bit low. Okay, how about this? That's really good. Something that's really nice, in fact, is that you have to worry about these bumps and wiggles in the solution of the Jeans equation. There's a term for the derivative of the surface density profile. And we always just assume it's a smooth exponential. When you do that, there's a big tension between the interstellar rotation curve and the stellar rotation curve of Gaia. If you put in the bumps and wiggles that are inferred here, that just goes away. Same rotation. The other thing I point out, these inner points are from the VVV survey of stellar motions, working out the effective circular velocity in the inner regions. I didn't fit to that. I'd already accounted for the bar mass, go right through the data. Well, that's pretty good, I would say. There is something weird going on in the DR3 data out here, but it's pretty good with the halo data out to the LMC. Then it's not, but the LMC is surely perturbing us in some way, so I'm not too worried about that. So if I want to be a positive, I'm like, wow, look, I predicted all that. Yeah, that model was out there. If I wanted to be negative about it, it's like, oh dear, there's a kink. The whole thing is wrong. Maybe, well, anyway. But that's an example of what you can apply the radial acceleration to extract more information than you might otherwise have. So we have these sort of three rules. The set of rules we know for planetary motion, named after Kepler. Galaxies do not follow Earth's laws, but they do follow their own set of rules. And the one we learned a long time ago is that their rotation curves approach something close to a flat velocity, not dv dr equals 0.000, but to a very good approximation. They stay flat indefinitely for a long time. And it's not just that. It's not just that we need dark matter to make rotation curves flat. We also need to understand why that amplitude of rotation correlates with the baryonic mass. And indeed, that the entire run of gravitational force can be predicted just from the distribution of baryons that we observe. That is weird. If dark matter is dominating, that just shouldn't be the case. Both of these quantitative relations involve the same acceleration scale. Here it's where the radial acceleration bends. Here you can rearrange this in terms of an acceleration scale, and those numbers are the same. Didn't have to be, but apparently they are. So in addition to these three rules, there is an acceleration scale that is important to the problem. Okay, so I'm going to leap ahead now. I said from here to eternity. We've been talking about galaxies here. I want to talk about stuff at high redshift, and a lot of people here I know are working on this as well. Oh, you know, I'm getting ahead of myself. I want to get that far, but I've shown this pretty JWST slide of lensing to remind you that gravitational lensing happens. And so I'm going to highlight here the work of my current postdoc, Tobias Bell, who has used gravitational lens data to extend these relations I was just talking about. So we're still talking about here, not high redshift. Okay, so this is something that Brower et al. Pointed out a few years ago, that if you take galaxy survey like you kids, you can stack bin and stack galaxies and mass bins and infer the potential way far out. A lot of technical details there I don't have to go into, and I'm just going to trust that they did it right for the purposes of this talk. I always hear that, but good enough. So what Tobias did is actually work through the math. There is an approximation that is made in the lensing community, which going through the math, I understand why they stopped the lensing level of approximation that they do. Being a nerd like many of us, Tobias pushed further, and a lot of the terms canceled, and you ended up with a very much nicer mathematical form. Really satisfactory. So he said, okay, well, let's apply this. And I said, well, that's a good sample. Let's try that. And this is the radial acceleration relation that he drives. The gray points are what I showed you before. They overlap with the gold points, which are the lensing there. And it's basically just continues along the extrapolation of the fit that we made earlier. Before, you know, you got down where there was a clear thing, but you didn't really know what the slope was beyond that. Basically, the extrapolation of the function we had assumed. And I want to emphasize that this is continuous over many decades in acceleration. So again, observe predicted acceleration in the high acceleration regime. We're in the solar system. Here we are in this room. Here are the orbits of the various planets. All the way out, there's Pioneer, and I have plotted the famous Pioneer anomaly. See how big it is? Doesn't really matter if you believe that or not. It's just not anywhere near this regime that we're trying to probe. And this thing goes down systematically. And the other thing I've done is split the galaxies by type, because there's been some discussion of the same or parallel relation for early and late type galaxies. We have both kinematic data for both types and lensing data for both types. Can't tell the difference. So it looks like a universal relation for all galaxies. Individual. Now that particular fade-in slope, right? If you continued down the dotted line, that would be Newton, and so you would get a Keplerian decline in your rotation curves. The particular slope of this line corresponds to flat rotation curves. So the fact that we're going to very low accelerations here implies that rotation curves stay flat very far out. So let's see how far out that is. And so Tobias has an FJ letter about this, which I encourage you to go look up. Here are a couple of galaxies with pretty extended rotation curves by the standards of H1, which typically go further out than you can do optically. And, you know, that's tens of kiloparsecs. That's way far out. The lensing, now it's been many thousands of galaxies binned up to do this. It's no longer an individual galaxy, but something of comparable amplitude. And that rotation just stays flat out. And beyond, I decided to cut off here because this is the separation between the Milky Way and M31. All these galaxies are selected to be isolated. If you do it for M31, then of course you wouldn't get this because you overlap with the Milky Way.
Just ask
Yes,
a
please.
quick question. So how do you get from data to the velocity?
So that is the magic of his formula, but you take the excess surface densities that are observed, and that actually maps pretty cleanly into the acceleration. So the more fundamental mapping, not entirely perfect, but the more fundamental mapping is there. But then it's just V squared over R. So if you know the acceleration, you can go back to the implied circular velocity, Bloodwood as particle to the particle at potential. And that's only true for isolated galaxies, right? And that's something Tobias wants to explore. But it really does seem to stay flat indefinitely, and if you, I think we have to believe the data out to 300 kpc. Brouwer did a lot of work trying to figure out how far out we could believe that, and that's a minimum. To make a long discussion short. In our analysis, there's no reason to disbelieve it all the way out to 1 megaparsec. At that point, the next plot. At that point, the systematic errors that we know about start to blow up, and that's dominated the known unknowns. You never know about the unknowns, but the known systematic is that in Tobias's closed form formula, you have to integrate from 0 to infinity. So you have to assume something about the behavior from the last measurement. And what he does is that it's okay, the maximum signal at the last point, 0 between that. And that's what these gray bands are. So out here beyond a megaparsec, it becomes uncertain, but it's really not clear that it's a problem for that. So now you see there are 4 here. These are binned up by mass. There are enough objects that you can do that. You can bid by mass, you can bid by type, you can actually start to ask questions. And one question we asked is, okay, it's pretty clear V flat there. How does that fall on Tully-Fisher? It falls smack on Tully-Fisher. Same relation. Just measured much further. Okay. So I was not surprised that this happens. I have more material than I have time for. It's okay. Now we're going to leap towards eternity, or at least very early times. So as a reminder, in the standard full dark matter paradigm, the dark matter is growing linearly. After decoupling, the baryons fall into that, and we get large scale structure. Nice illustrations all the way back from Tram in 1992, where he also complained about, geez, there are quasars at almost redshift 4. God, how can that be true? And it's hard when that growth is linear. It takes time for growth to here. And so here is one of these famous merger trees where you start out with little subhalos. Times are probably impossible to read, but here's back time of 12 gig a year here, 8 here, and things merge and merge and merge to make big galaxies at late times. At early times, they're in all sorts of little clumps. So remember that time and redshift are inversely related. We're obsessed with getting to higher and higher redshift because it's cool. But you're dealing with less and less cosmic time. So for a vanilla Lamborghini cosmology, that's about total age of 13.5 billion years. Light gray bands is the first half gigayear, the darker gray band is the next gigayear. So redshift 9 already gets you back to that first half gigayear. More like redshift 4 is that next gigayear. So 4 sounds a lot less than 10, but it's all early universe, give or take, right? So it depends on what you need. But you know, talking about that region there. Here are some more examples of merger trees. This one from the TNG 50 simulations. Again, you see the same thing at early times. Now it's marked out in redshift. So this is redshift 10, redshift 6. And at that time, one expects there to be a whole lot of little subhalos, not individually bright galaxies. Even the largest progenitor is pretty small early on because it hasn't had all its mass built yet. So when we're worried about explaining bright galaxies at high redshift, there are actually two problems that are coupled together. One is the evolutionary part that we're all concerned with as astronomers, form stars, how does their luminosity evolve? But the more fundamental problem is how do you assemble mass? And that is inherent to the paradigm, right? So there's another illustration of it. I got interested in this because former student Jay Frank wanted to do a thesis looking for protoclusters in the high redshift, and I sort of channeled my theorist friends and said, well, there are no clusters of high redshifts, but you know, not here for that. And he found things, right? Things that are associated in the sky and are spikes in the redshift distribution. So these little X's here, not close enough in redshift, even though they're close enough on the sky, but all those black points are at that same redshift. There's a nice cluster there. And this thing is a redshift 3, right? You shouldn't have things there. And he found a lot of such candidates, enough that he could fit Schechter functions to the cluster galaxies. And so here are a bunch of fits. They include some really bright objects. So you say, well, maybe that's AGN contamination. Let's just ignore the really bright things and fit the rest of the data, and you can get the characteristic magnitude out of that. So we're already hedging. We're already throwing out the brightest things when they do that. And when we then plot that up, here is the apparent magnitude, 4.5 microns. So each point here represents lots of galaxies. That's L star for a cluster of population, or a protocluster, whatever you want to call these groups. Work that other people did in different colors, the dark blue and the black. J's are the light blue points, and he kept finding things out to above a redshift of 5. And in his paper on this, there are a zillion population lines and all sorts of evolutionary models, but the only one that was really interesting is the one that I expected nothing from. When he first started doing the modeling, it's like, okay, reality check, build an exponential model. Just the dumbest thing you could do, right? But have all the stars forming with a simple thing. Started at redshift 10 with an e-folding time of 1 gigayear, because we were all doing this in 2017, 2016. So it was like, okay, no way you'd have galaxies forming this big earlier than that. So this is sort of the dumb limit, and it really looks like the data for the other models. One of the other things that he did then was apply the algorithm he was using on the data. These are all spectroscopically confirmed knowledge. On a look back cone in the Millennium simulation. And so those open squares are what he gets from analyzing the simulation. The orange line is the right answer known from the simulation. So basically, we can tell the difference. The same algorithm sees something different in the simulation than what it does in the real universe. And it's no mystery why this is. It's because by redshift, and galaxies should have been subdivided in sort of all sorts of little chunks. Right, that is why galaxies are getting fainter here so fast, because they're also getting subdivided at high redshift. And the data just look like this monolithic model. So here's one particular subhalo from TNG 50. This band illustrates the 2 sigma range of the average star formation history from the illustrious suite of simulations. This particular subhalo is that jagged line. And that monolithic line is what fits the data. So what we have to do if we're going to explain these high redshift observations, somehow turn that line into that line. And it's basically what a lot of people are trying to do right now, just by invoking different information efficiencies, IMFs, etc. But real problem is this. That's they shouldn't have all that mass invested in a single object, but that's sure what the data look like. So this is now the same data transformed from observational magnitudes into the equivalent stellar mass. So same line, added a little more data, but basically those are all the same data. Looks very much like that line, looks very much not like what the simulations predicted ahead of time. And the reason isn't because they got their star formation histories wrong. I think it's because the mass assembled much faster than we expected. So babble on about that for a long time, but I will just include this funny note that in February, Physics Today wrote a story on these high redshift observations, including this quote. JWST is revealing far more bright galaxies in the universe than anyone predicted. When JWST launched, I wrote this blog post. What do I predict? Big galaxies at high redshift. So I guess I'm not anybody. That is exactly what I predicted, and I'm sorry I didn't get as far as telling you why I thought that, but there's a long literature on this, and there are follow-on predictions. Basically, I think this is driven by the same theory that drives the puzzling kinematic observations I described, which is MOND. Sorry, it's not my damn theory, but I keep testing it and it fails some things, but it predicts a lot of things that we don't understand otherwise. And one of these is that Bob Sanders said, okay, if this is what's going on in the early universe, how long would it take a ball of galaxy mass, ball of gas to collapse? And it's a few 100 million years. So you should have massive galaxies at Z of 10. This is why that prediction was made a quarter century ago when JWST was just getting started as a project. There are other things. Basically, all of structural formation happens faster. So you should see high clustering among the quasars. So not only should you get bright quasars early on, but they should already be clustered. Rich clusters form quickly. Ionization gets started early. Not that it can be very patchy, but I would think it would be something like higher than that. And that is all I think I should take your time for. Thank you very much. Stop. Share. No, still going.
We have a fact.
Okay, so we're getting kicked out.
No, we have.
You guys are leaving.
Selves out.
Okay. If any of the students want to ask a question, we could probably do 1 or 2 questions.
We have to.
Sorry, I should have stopped. Yes, question. Yes.
I wonder, so the cluster combination is start down redshift 2. And some of the high redshift way that we want, would that be they are actually BCG?
Sure. Yeah, a lot of times you see that kind of activity in BCGs, and in fact, the thing that got Jay started on the project I described was actually a preceding project that Jim Calvert and I did, where we looked for clusters around redshift 2 for reasons but basically went and looked for, some kind of activity. Okay, we have a redshift. Are there things nearby? Okay, there are. Do they have redshifts? And so if we identify, basically it's the old 3C search. If you find a lamp post and other stuff around it, maybe it's a cluster. And those were actually easy to find. And I remember giving this kind of talk like 15 years ago and say, geez, there are these clusters of redshift 2. And people are like, well, there are no clusters of redshift 2. So yeah, very much. Oh, your bosses have left. You can ask me. This is scary stuff, right?
What kind of X-ray instrument what kind of resolution on the X-ray instrument you need to see such clusters?
That's beyond my capacity. The X-ray, refractive falls off really fast cosmologically, so very sensitive. But I don't think you need great resolution. You just need the sensitivity. I think you'd like enough resolution to tell it it's a ball and not a point source, obviously. But beyond that, which is a related question: when do clusters get their gas? Obvious to me. The hierarchical structure formation happened much faster than in lambda CDM. Maybe it got very early. But so yeah, I don't know, but it'd be a good thing to. Since you raised the point, I will mention that is Jay's data for velocity dispersions of clusters. The point size basically correlates with his probability assessment. The big blue ones are very certainly clusters. Light blue ones, probably. The gray ones, probably not. But there is a velocity dispersion of typically around 600 kilometers a second observed in these things up to redshift 3. And if you do, again, the same experiment apply the same algorithm to look back cone, then you get a number of half. So these objects have internal motion that are higher than predicted. So it really does look like a lot of about this light. The mass was a symbol early. That's the key thing. Is we need probes of mass. You can do whatever you want with models of how the body moves, whatever. But there's a lot of flexibility. I talked to some of you earlier. You asked the traditional question here, I guess is what older me would have told younger me, which was don't work on Mond. And sociologically, I still think that's a good response, but scientifically, it's been incredibly fruitful. I mean, it's really enabled these kind of predictions, and it's the only theory that got these things right in advance. That is telling us something. Maybe it's telling us something about the nature of dark matter. Maybe it's telling us that we're marking up the wrong tree with dark matter. Regardless, I think there's still fundamental science to be done here. We do not yet know all of the answers, and that's really wonderful, really. It's not just going into the 6th decimal place. Any other questions?
Are there any other questions? Otherwise, well, thanks, Stacy, again.